And example 1 is a wide open question. You want to write the first 6 terms of an increasing, so that's one important word here, and arithmetic, and anytime it says arithmetic, that tells us that there is a common difference. We're adding something the same amount each time to get the next term. Okay? So, we want it to be increasing. So we have to start somewhere. Sam, pick a favorite number. 2. We're going to start at 2. It needs to be increasing. Does it make sense that your next number is going to be bigger? Okay? Kara, how much should we add each time? 4. So if we added 4 each time, you see that the second term would be 6. And then 10, and then 14, 18. And we've written 6, the first 6 terms, it's increasing. We pick 4 for D. So we would say the common difference is 4 because in each of these we're adding 4. And we have made an increasing arithmetic sequence. In B, we want it decreasing. Destiny, pick a favorite number. 17. And now we're going to be going down by a certain Adam. How much should we go down by? 2. Go down by 2. So if we went down by 2, the next one would be 15. This makes it decreasing because you're going down. And if you're going down by 2 each time, so this time we're going down by 2, then the next one will be 13, then 11, then 9, then 7. And thank you for being nice, right? You could have been like, oh, I'm going to get Mr. JR here. I would like you to go down by 3.872 each time and make me struggle with the mental math as I have to do my decimals all the way. So it was very nice that you said 2 to keep things simple, right? So in this case, our common difference would be -2. One of them is increasing, one of them's decreasing. So what's going to happen is we're going to make a video like this one. We went through the example. The textbook always has another example right beside it that they've provided. Okay? But the problem with an example a textbook provides, they have to have so many more words and stuff like this. By doing this together, you now see what you would have to show. If something like this was on a quiz, you know what you would have to show to get it right. But you can also, if you want, read the example beside. After we're done a question, I'm always going to get you to circle a couple of questions from the homework. And sometimes I'm going to give you time right away to start them. Today we're going to do example 1 and then 2, and then I'm going to give you some time to try. So turn to page, if you right after this assignment, turn to page 8, and you see the exercises. And since I said 4, 5, and 7, what I'll get you to do is I'll get you to circle 4, circle 5, and circle 7. Okay? This means later on, if you go home, you will always, and go to your homework, you'll be like, are there any I didn't finish in class? Then you'd be like, oh, I should try question 4, question 5, question 7. And they have this space right in the textbook. You write your answers right there. Really nice. Also, you'll notice in this book that if you turn to page 13, most math textbooks put all the answers at the very back of the book. Are you used to that? Right? So you're like, you have to like, swoop, and then you look at the end of it, swoop, all the way back. Okay, this is really nice because they always put the answers just at the end. So you don't have to flip as many pages to check your answers, which is really nice. Okay? Now at the bottom of page, so we're going to do example 2, and then I'm going to give you some time to work on the questions that I get you to circle. Another thing that some people like to do is, you know how we circled question 4, 5, and 7? Some people like to write above example 1 that we just did, 4, 5, and 7. So if you got stuck on any of those questions, you could look back at your notes and be like, oh, this was supposed to be the question that helps me figure this out. And sometimes you're going to run into questions that you have and so I'm going to get you to take out your highlighter again because at the bottom of page 4, and we talked about this already, we have this idea. Okay, so this word is going to come up, this idea is going to come up. It says, consider an expression, consider the arithmetic sequence 3, 7, 11, 15, 19, 20. To determine the general term, we can use a pattern. Okay? And there's 2 ways to look at it. And I showed you both of these already on that sheet that we did before. So we could look that term 1 is 3 plus 0 fours, because it's just 3. Term 2, you would add, right, to get to term 2, you'd have to start from the first term and add 4 once. To get to term 3, you would have to add 4 twice. So using this pattern, if you kept on going to the general term, Tn, any one of them, and sometimes, and I think if there's space in there, sometimes I find it's really easy to see what to do if you do a big number like 100. Does it make sense that term 100, using this pattern, would start at term 3, and you would have to add, start at term 1, which is 3, and you'd have to add another 3 99 times 1 less. But by using a big number like 100, the pattern is really easy to see that that number there is 1 less than 100. Does that make sense as far as patterns go? So as a result, it's not, sorry, I got it, doesn't make sense because it should be 99 and what's the common difference is 4. You're adding 4 99 times. Does that make more sense? 1 less than 100. So when we go to the general term, this is 1 less than n as an idea. Okay? And they take this and actually have your first formula on your formula sheet, which is right here. Right? I'm going to go back to that and show how that formula works. So any term, the general term, will always equal the first term, which we can write as term 1, plus the common difference, which is d, times by 1 less than n minus 1. So what mathematicians do is they say, let's look at a pattern Does this pattern work for every sequence, every arithmetic sequence? Yes. If it works for every arithmetic sequence, what are we doing every time? Every time we're looking at what the first term is. Then we're looking at how much we add, which is your common difference. And you always have to add it one less time. So you have this formula, and most of you will start to like to use the formula because it's on your formula sheet. And it's sort of one less thing that you stick in your brain because it's on your formula sheet. However, remember we also were able to do this, and you're able, if you want to use the shortcut every single time, that's fine as well. The shortcut says, if I have term number and the value, so term number 1, 2, 3, 4, which in this case was 3, 7, 11, 15, we know that our slope is 4. That's the same as your common difference. And if this makes a straight line, you know that it's going to be y equals mx plus b. You know that the m is 4. And what would make it work? Minus 1. So that makes our Tn 4d minus 1. Sorry, not 4d, 4n. Oh my goodness, sorry guys. 4n minus 1. Because the d is the same as the slope, that's our 4. 4x minus 1 is the line, so it would be 4n minus 1. Can you see that this one and this one, are they the same? They're written differently, so they don't look identical right now. But are they the same? What would I have to do to the formula here with the common difference? I'd have to distribute my 4, right? 4 times n would give me 4n. That matches up perfect. 4 times a minus 4 times a minus 1 would give me minus 4. Like term with plus 3. Does that give me a minus 1? Yes. So you're able to use, if you want to use that shortcut for y equals mx plus b as a shortcut, perfectly fine, right? Then you're using your mind because the shortcut's not on your formula sheet. But this is on your formula.